All right, everyone, so we're going to work on integration by parts right now. And with all integration, what we realize is that there's no formula to always integrate. You have to recognize the type of the problem and then determine which method is most appropriate. And so in order to do integration by parts, it stems from the product rule. And I know that the product rule says the derivative of uv dx is equal to u times the derivative of v dx plus v times the derivative of u dx. And so that's the product rule. If I want to do integration by parts, what I'm going to do is I'm basically going to undo the product rule. I'm going to integrate. And so if I'm going to integrate this, I'm going to integrate this dx, and I'm going to integrate this side as well. And I can integrate each part individually, dx and dx. And when that happens, I can then come along and I can cancel that out, which leaves me then with just uv equals, and I can also cancel the dx out here, and I can also cancel the dx here. And so then I'm left with the integral of u dv plus the integral of v du. And if I rearrange this scenario, I'm going to have this on this one side equals, and so basically I'm going to go uv and subtract, so basically I'm subtracting this, so it's a positive u times v minus a v du. And so this is our formula for integration by parts. And if you look at your formula booklet, this is what you're given here. This is what you're given here. And the key to integration by parts is choosing very carefully what is going to be your u and what is going to be your dv. You will differentiate, and the dv you will integrate. Okay, so choosing u and v is very, very important. So let's do an example here. And when I'm going to choose my u and v, typically I want to differentiate either the polynomial or ln x. And those are just a rough guideline. Of course, there's rules that break this, but whenever I see the polynomial or ln x, that's the one that I'm going to choose to differentiate. So let's consider this example here. I have integral of x cosine x. These two are multiplied, and so I'm going to let my polynomial, which is x, be my u. So u is equal to x. And I'm going to let my dv equal to cosine x dx. And where that comes from is if I look at my formula here, let me call that back. If I look at this formula, in my integral I need u and I need, here is what I like to look at, I need u and I need dv. Well, here is u, here, and then dv is all of that. So here's my dv, and I've broken it up as such. So once I have my u and my dv, what I can then do, I then come along and let me move this formula out of the way for a bit. I take the derivative of this, I go du dx is equal to 1, and then I'm going to multiply by the dx, so du is equal to dx. And over here, I'm going to integrate this. So I'm going to integrate this side and this side. When I integrate dv, I simply get v. When I integrate cosine x dx, I get sine x. Then I go back to substituting with my formula. I know that I need uv, u is x, v is sine x, minus the integral of v, which is sine x, du, which here is dx. Note the variables correspond properly. And so now I have x sine x minus, I'm going to integrate sine x. Well, the integral of sine x is negative cosine x plus c. And so I end up with x sine x plus cosine x dx. So using the formula, I choose my dv carefully. The polynomial or ln x are my preferred choice for u.